Good. I'll be quiet.
No, heckler's are welcome.
Yeah. I have to write within the brain words. It is a problem.
That's more. More for us. Thank you very much. It's really bad about not having power.
That's on my heart.
I
Mr. Bird. Dr. Bird.
That's me.
We have doctors in that family too.
That was my name when I found.
Oh, yeah, yeah. If you'd be bonding with them.
Yeah, no.
Heart gas.
Yeah.
My
Don't
younger,
ask me to do anything medical.
no.
I mean, the result will be catastrophic.
Yeah, yeah. You'd probably be the last person to ask. Interesting. Now that you mention it. My youngest brother lies, that's his professor at Montana State University.
Right, yeah.
My father-in-law was a professor at Pennsylvania in photography.
Nice.
Yeah, yeah. It was a side discipline. It was a side passion of this. Because it's for 100 years. And my wife is a computer science engineer with a major in physics. I know what right angle. Easier to and April 8th is going to be a big deal.
Oh, yes.
Yes. They are so excited that side of the
Well,
family.
I had booked my flights.
Yeah.
So I'm leaving on Saturday.
To be in.
And then discovered this booking of this here.
Yeah, exactly. Yeah. But the weather is going to be bad here. The span.
Oh, was it? Oh, yes.
I just,
I was lucky. I saw it in 1999 in London.
yes. The next one is in 20 hours.
Yeah. Yeah.
So Dr. Neal, it's a 30-minute slot, but it's lunch after this, so.
You guys hungry?
Not really.
No, that's really
Breakfast, so.
Yeah.
that's really good.
That was a gargantuan burrito.
Yeah, that will be,
only eat half. Yeah.
Right.
So a little bit about our audience today. We have our very esteemed customer for Ultra Plastics that is here today to listen to you. And so we have John Zink, who's interested in John Zink worked on the Chenier project a few years ago. So I think it's another universe and more on
Okay, great.
applications and new advancements in the field. So just
Good.
a quick introduction so you understand who are the customers in the audience.
Right.
today.
It's 5 minutes. My 30-minute slot gone already.
Right.
Oh, good morning, and thank you very much for taking the time to come and listen. I appreciate it. I'm Neil. I'm the chief scientist at Fluenta. So if something goes wrong, it's not my fault. It's someone else's fault. If it goes well,
Always.
just approach me. Yeah. So what we're going to talk about is the measurement of flare gases containing CO2. Now, what you're going to hear me say several times through this talk is that CO2 strongly absorbs ultrasound. It's like trying to shoot a pea through a brick wall. It just doesn't go through. And this has always been a challenge, and this is what we've been focusing on to try and get to the point where we can measure in high amounts of CO2. That worked. Yeah. So, quick agenda. I'll just talk a bit about flare gas measurement. You guys probably know much more than I do. So if I'm wrong, you can tell me. Then we'll look at some flow measurement methods. So not ultrasound, which I'm going to focus on, but some of the others, just to give you a kind of a scene of what measurements there are around. Then we'll look at the ultrasonic flow measurements and then dive right into CO2 and understand what the problems are. And then I'll show you some results from the most recent testing we've done. And we'll talk a bit about other gases as well, because the world isn't full of just CO2. So CO2 in flare gas, mostly when you talk about flare gas, you think of hydrocarbons, perhaps some nitrogen in there, a few other gases. But what we're seeing is many requests for measurement of flare gas that contains a lot of CO2. And these are just some of the sources of CO2. It's going to be there, depends on the kind of well you've got, and then downstream the kind of processing you're doing. I mean, for example, if your processing is a synthesis of ammonia, then you're generating vast amounts of CO2, all of which have to be measured. So why is it important? Well, how can I condense into one slide the 288 presentations, was it, that have happened at this conference? So I really don't need to say why it's important. It is important because if we can't measure in CO2, we can't do accurate measurements at all in gases which contain CO2. And if we can't measure, then we can't meet the regulations, and then we get problems. So that's the reason why it's important. And flare gas it's an interesting thing to measure because it's not constant. It's approximately atmospheric pressure because you've got an open pipe at the end, so you don't see much different from atmospheric pressure. But you tend not to know exactly what the gas composition is. So you have a good idea because the plant will tell you that, but typically they'll say it could be this composition or that composition or a different composition depending on what's happening in the plant. So whatever technique you use to measure flare gas has got to be able to cope with varying gas compositions. We'll have huge temperature ranges from LNG down at -160 centigrade right the way up to industrial processes which are 250, even 350 degrees C. So the equipment we put in the pipe has to be able to cope with those wide temperature range. And as one of the presentations earlier said, we have these huge turn down ratios. That's the difference between, or the ratio between the lowest and the highest flow you can measure. And again, that brings challenges to the flow measurement technique. So all in all, it's a pretty challenging gas to measure. And it gets worse when you include carbon dioxide, like we see here. So this is a request from a customer to measure a gas. You can see it's a thermal oxidizer application, and they want to measure 96% CO2 in a 12-inch pipe. If I was standing up here 2 years ago, I'd be saying, thank you, but we can't do that. Now I can say, yes, we can do that, and we'll talk through how and why that's possible. So let's look at some of the flow measurement techniques. So here's a menu of some of the more common ones, if you like. I'm not going to talk through all of these. I'll talk through a couple of them. But the key takeaway here is that there's no panacea here. There isn't one flow measurement technique that's going to cover all your flow measurement requirements. Each of them have their own areas of what's the word? Focus, if you like, yeah. And others, they cannot do certain things. So it's a question of horses for courses. So it's really got to be, you look at your application and you pick the flow measurement technique that matches it best. So let's look at differential flow measurement. This is a very common technique, quite straightforward. So somehow you put a restriction in the pipe. It could be an orifice plate like this or something else. As the gas goes through the pipe, through the restriction, it speeds up and you get a pressure difference. And you measure that pressure difference, and from that you can calculate the flow. This, in fact, isn't a great technique for flare gas, because the point of having a flare, among other things, is to cope with dangerous situations where you've got to get the gas out of the plant. So the last thing you want to be doing is putting in a restriction like that. But it's a very common technique, can be very high accuracy if it's installed well, but it doesn't have the turn down ratio. You might be lucky to get to 500 to 1, and that's because for the physicists in the room, there's a square law relationship between pressure and flow, and that limits the actual turn down ratio you can achieve. Coriolis mass flow meter. Now, this is probably unique in that it measures the mass flow directly. The other techniques measure volume flow typically, and then from the volume flow, if you know the density, you can calculate mass flow. This does the mass flow directly, and this is the technique that API ask you to use because they want a direct measurement of the mass flow, not the volume flow. So it works by sending the gas through a small tube. You vibrate the tube. That causes a twisting motion in the gas, which then changes the phase of the vibration of the tube. And if you measure that phase difference, you can work out what the flow is. It's a highly linear technique, so that means it can be very accurate. It's expensive, And it's not good if you've got lots of vibrations, as you often do on installations, because you're measuring vibrations. So you've got other vibrations there that can perturb the measurement. Then thermal mass, this is another technique. Here you've got gas flowing over a heated sensor and an unheated sensor. So the heated sensor, you put heat energy into the gas, and the gas is taking energy away from the heater. And then you keep a constant temperature between the heated and the unheated sensor. And from that, you can calculate how much gas is flowing over the heated sensor. But you do need to know what the thermal properties of the gas are. Therefore, you need to know the gas composition. It's an easy installation, but in common with other of the techniques I've mentioned, they're intrusive. You've got to put something in the pipe. And as far as possible with flare, you don't want to do that because of the safety implications. Characteristics of some of the technologies, you can read this when you get the PDF. I'm not going to go through that in detail. You are good. And then I put it for ultrasonics down here. It's accurate and reliable. It has non-intrusive sensors, important for flare gas, but it's got challenges. CO2 we're talking about today. Perhaps next year I'll come back and talk about hydrogen, which is equally challenging for ultrasound. But if we zoom in on the requirements of flare gas measurement, then 3 of these aspects come to the fore. You want a non-intrusive design, so that kind of cuts out the ones in the middle there. We need to be able to handle changing gas compositions, because we know the flare gas composition changes and can change very quickly. And we need a certain level of accuracy. So these are typical accuracies for these techniques. For ultrasound here, I'm focusing on ultrasound meters for flare gas measurement, the kind of meter you have. I'm not talking about custody transfer, which is a lot more accurate than this. But then that's just a different ball game altogether. So these are the techniques, and you can see ultrasonics is non-intrusive, handles the gas compositions, and has the kind of accuracy that's needed for flare gas measurement. Right, ultrasonic flow measurement. Button up your seats, let's go for it. So what's the big problem? Well, it's all about measuring how long it takes to get from A to B, and then from B back to A. Simple. But to get the accuracies we need, we've got to measure those times down to the order of nanoseconds. Put that into context, a nanosecond is how far light travels, how long light takes to travel 1 foot. So it's a vanishingly small amount of time, and that's the kind of accuracy we need. So how does it work? Well, we have the pipe and the flow going through the pipe, and we've got the two transducers, and we send an ultrasonic signal in one direction, say take the yellow direction first, the downstream direction, and that signal gets speeded up as it goes across the pipe because it's going with the flow. When you transmit the signal in the other direction, you're now going against the flow, which means it gets slowed down. So you've got one fast and one slow path. And from those 2 measurements, that's how we can calculate the flow. Achieving that is reasonably straightforward. You generate a signal, you amplify it, send it to the transducer, and then it comes back. Amplify it again. You've got to do that carefully because they're very small signals. And then we've got the received signal. And once we've got the 2 signals in some kind of digital form, we can do the processing to calculate what the gas flow is. And these are the basic equations. They're a little bit simplified, but they're the basic equations. But the key takeaway here is you don't see anything about gas composition. So we can calculate the average flow and the velocity of sound just from these two times that we measured, the T up and the T down times. Nothing about gas composition. So how do we do it? So this is the signal we're transmitting. It's a single frequency burst of ultrasound. So we send that out. Then it crosses the pipe, and this is the time it takes to cross the pipe. Then it comes back again. So we've got to measure that time there to an accuracy of a few nanoseconds. That on this scale, that's a millionth from there to there. That's the kind of accuracy we're talking about. This is in the ideal world, and it's pretty straightforward. You can probably recognise you could easily measure that time difference there. But we don't live in an ideal world. And the first problem we have is that the transducers are not ideal. The transducers mess up your signal, they're filters. So you think you're sending something like that. That's the electrical signal you're sending. It gets transferred to sound, goes through the pipe, then goes from sound back to an electrical signal. And you get something like this. So all of a sudden, the nice sharp edge that we had before where we could do the measurement is gone. It's kind of starting up slowly. So the way that is measured, and this is a common way of doing it, is like this. So I've zoomed in here on the beginning, and you can see the signal starting to increase it in amplitude, and you set a threshold. And once the signal has got past that threshold, you say, that's it. That's the beginning of my signal, approximately. Then you use some other techniques, which I won't talk about today, to find out exactly where that waveform starts. So that is generally how it's done. But in flare gas, we can have carbon dioxide. That absorbs the signal. That means very small signals. Right. So we've got very small signals. That means we've got noisy signals. And this is what the signal looks like. This isn't actually that bad. It gets a lot worse than that. But you can still see where the signal is. Yes. Yeah. It's two things. The transducer is a bit like a microphone. So you're listening for the signal you want, but it's picking up all the other sounds as well. So any sounds like things like whistles from valves or what have you upstream or downstream, that can add to this noise. And then there's electrical noise. You also have noise in electronics, and these signals are so small that the signal just starts to drop down to the basic noise level. So that's what the signal looks like. Now, if I zoom in again, that's what you get. So the threshold system doesn't work very well anymore. If you look over here and you squint, you can go, yeah, I can recognize there's some signal there, but where does it start? It starts somewhere here, but we can't tell. So that's just puts into context the kind of challenge we have. Let's look a bit at the impact of CO2 now, because this is where things start to get worse. So here what I'm showing is signal level. This is the signal size, and this is the pipe size. So as the pipe gets bigger, the signals are going to get smaller. This curve here, this is nitrogen. So that's a fairly easy gas. So it's absorbing the signal, but as the pipe gets bigger, the signal doesn't get that much smaller. So this is only the gas absorption. I'm not talking about diffraction or other effects. Then when we put CO2 in, this one is only 10% CO2. So already you can see it's having a dramatic effect on the signal size. And when you get up to say 30% of CO2, the yellow curve here, by the time you get to a 24-inch pipe, you've already lost 99% of your signal. And that's only with 30% CO2. We're aiming for 100% CO2. So that 1% gets a lot less than that. So that, in a nutshell, captures the problem. We're just losing signal because of the absorption of CO2. So addressing that, there are probably three ways you can do it. One is, well, let's just generate more signal. Just turn up the wick and create more signal. The second one is to put the transducers closer together. Just on the graph, if they're closer together, you get bigger signals. And then the last one is to optimize the signals for this noisy environment that you've just seen. Transmitting the signals, increasing the power of the signals, yes, it works, but it doesn't give you as much as you think it's going to give you. You're limited anyway by the safety rules, the EX rules, on how much power you can push into the transducer. So I can't just turn up the signal by 1,000 times. You're not allowed to do that. In this example, the blue curve is showing the signal. We've got, this is the CO2 content on the bottom, and we've got the maximum pipe size on the vertical axis. So 30% CO2, you can do a 35-inch pipe maximum. And as the concentration of CO2 goes up, the pipe size goes down. Now, the orange curve is where I've doubled the size of the acoustic signal. That means I've multiplied the power by a factor 4. And you can see at 30%, it's only giving you about 3-inch increase in pipe size. And when you get to 100%, it virtually gives you no improvement at all. So yes, always generate as much power as you can, because you want the biggest signals that you can use, but it isn't going to solve your problems. Pushing the transducers in, reducing the separation, that helps, but that means you've got an intrusive system. So if you've got a big pipe and you push the transducers in and a very high flow, the pipes are going to start to wobble, could break, and it will compromise your measurement, even with the vibrations from the pipes. An alternative way of doing this is to put the transducers in from the top of the pipe, so you're not going across the pipe. So as the pipe gets bigger, the transducer separation stays the same, so your signal size stays the same, so that's good. But you're only measuring part of the flow. When you're going across the diameter, you're measuring the complete flow. When I'm measuring up here, I'm missing out all of the main part of the flow here. So I'm doing a kind of a secondary measurement, and I've got to calculate back to see what the flow is. So that can cause increased errors. So not the best way to do it, if you can do it without being intrusive. And you see the presence of the sensors here, it perturbs the flow. So this is a nice clean flow here, nice profile, and you can see what happens when it hits the transducers, it messes up the flow. So you're measuring a messed up flow, not the flow that you want to measure. So that's pushing the transducers in. So what about the signals? So go back to the signals again. So this signal here, this is different to what I described before. Before it was one frequency. This time we're putting a range of frequencies. It's a chirp. You start at a high frequency, then go down to a lower frequency, just like listening to birds chirp. Exactly the same thing. So that's the signal, and it has some remarkable mathematical properties, which I hope to show you. So back to our transmit receive. Here's our ideal transmitted signal. Here's our received signal, and there's the time of flight as before. These are with the multiple frequencies in it. Then when you receive it, you put it through a calculation called correlation, and you get a curve like this. And the peak of the curve there tells you exactly where the received signal is. And that works fine. So what happens if we've got noise? Well, there's the noise, the same amount of noise as we saw earlier on. It's hardly changed the correlation curve. X still marks the spot. But that noise, that's the kind of noise you would see when you've got 30% CO2. Not that difficult. What happens when you've got 100% CO2? Then it looks more like that. So now your signal has just gone down into the noise. Yeah, you could say, yeah, there's something there. But the correlation knows exactly where it is. X marks the spot again. So this is one of the techniques you can use just by optimizing the signal to be able to pull the signal out of a noise floor, as you see there. So what happens in real life? Well, this is the system. This is the flare phase system. So we have the transducers sitting in here. I'll talk about their characteristics in a moment. Some electronics here which drive the transducers. And then the rest of the system over here, this is very much like Fluenta's other product. So this guy here is doing all of the calculations and reporting the flow and handling the industrial IOs and so on. So I'm going to zoom in for a minute on the transducers and this electronics here. So we developed the new transducers for this system. The driving force was temperature, because we're going to cover this huge temperature range. the range you see here. And that really restricts the materials you can use, because you need materials that can work over that whole range. And then we started looking at CO2 and realized we needed something else. So we built into the transducer a sensor which allows us to listen to what the transducer is doing in situ in real time. And also we added a mechanism inside the transducer so we can fine tune its response to match the particular gas and the characteristics of the gas that we're measuring in. So we can listen to what's happening and then change it. And that's achieved by the electronics here. So this bit of electronics does some simple stuff. It increases the transmitted signal. Remember, bigger signal is better. So we try to do that. And it amplifies the received signal as close to the transducer as possible, because we want to minimize the noise. We don't want noise picked up on a long cable. So the amplifier goes there. And then what it does, while the system is working, every time it does an ultrasonic measurement, this thing is monitoring the transducer's characteristics. And it's adjusting the signals to match the transducer characteristic. So for example, if the temperature changes, the frequency of the transducer shifts. It can shift by a few kilohertz. If you don't move your signal with that, all of a sudden you haven't got a working system. So we have to listen to the transducer, listen to the frequency shifting, and generate the right frequency to hit the transducer right on its resonance. And then it uses the second feature in the transducer to be able to tell the transducer to change its characteristics a bit to better match the gas that we're measuring in. And then finally, it compensates for something called phase shifts, which can cause inaccuracies in your flow measurement. So that is really the brains of the system. So you've got the facilities in the transducer, and then you need a lot of processing power in this box to be able to always have the transducer operating exactly where you want it to be operating. So we needed to measure it. So we don't have a facility ourselves which can cover the whole range of CO2 and the high flow rates. So we got in contact with an institute in Brazil who built us a flow rig for this. So it allows us to do different amounts of CO2 in different flows. And we headed up there, I suppose down there in January, and we measured our system. I'll show you some results in a moment. And we're heading back in April, later this month, to do another batch of tests because we've learned from the original test results we got. It's a pretty colossal bit of kit, not something you'd have in your backyard. So the pipe diameters here are 20 inches. We can have different spools, so different pipe sizes where the transducers go in, so we can test those. And a range of flows here, depending on the spool size. In our testing in January, we got up to about 80 meters per second, and that's across a whole range of 0 to 100% CO2. And we were verifying the concentration of CO2 using in situ and ex situ instruments to make sure we knew what was in there. So this is a summary of a huge amount of results data. So in IPT, we had a 10.5-inch spool and we reached 99.1% CO2, only because we couldn't get any more CO2 in there. Back at base, we have another setup, which is a 12-inch pipe based, and we got to 94% CO2 in that. Now, if you take those results and extrapolate, then you get a curve like this. So this is pipe diameter, and this is the maximum amount of CO2. So over here, the smaller pipes, we can do 100% CO2. And if you recall the method of mounting where the transducers go in from the top, that is that point there on that graph. So with the transducers going in from the top, it always looks like a 9-inch pipe equivalent, even if the pipe gets bigger. But I mentioned about the problems, there are limits of that. But we can always measure 100% CO2 in any pipe size if we use this particular configuration. This point here is the limit of 100% CO2 when the transducers are non-intrusive, so going across the pipe at 45 degrees, as you saw. And then if we have methods of mounting the transducers differently, which enables us to get up to 16-inch pipe in 100% CO2. And that, I think, is the best in class. I haven't seen anyone who can do that. So that's a summary of those results there. But what about other gases? So I talked a lot about CO2. That's only one of the gases in the flare line. And as I mentioned before, when we get a request for an installation, we might get 5, 6 different gas combinations for different situations, blowdown situations, startup, shutdown, and so on. And we can't possibly measure all of those. I mean, we haven't got the facilities. I doubt if anyone's got the facilities to measure all gas compositions. So what we wanted to do was be able to go to customers and say, look, we can measure this, and this gas composition or any composition you have based on calculations which are based on real measurements. So we developed a piece of software here which allows us, from those reference measurements, like the ones I just showed on the previous slide, we take those reference measurements and we calculate through to any combination of 20 gases. So you just take n gases from 20 and say, this is my gas composition, and the software will say, yes, you can do it, or no, you can't. So what the software does, it takes, like the gas composition, like I've said, it takes the pipe diameter and the pressure and temperature of your measurement, and also the ultrasonic frequency, because that has an impact. And then it calculates what the absorption is using these various properties. And it also has a model of our meter. So it can say, well, the signal size is going to be this, and the characteristics of your signal processing allow you to do this amount of signal. And then it gives at the end a performance metric which says, yes, you can do it, or no, you can't. Just to give you an example of the kind of output it gives, this is big slide this. These are, take this table here. What that table is across the top, you've got pipe size, and this is percentage of CO2, and this is for a binary combination of gases. This is CO2 in nitrogen. So here, at this corner, you've got a small pipe, and you've got no CO2. Easy to do. So it's that green. On the far side, the top right, we've got 100% CO2 in a big pipe. And this is for non-intrusive measurements, so going across the pipe, and it says, well, you can't do that. We can't do a pipe the size of that. So it gives you the figures of merit, they're the numbers. Green means, yes, we can do it, no problem. Red means, no, we can't do it, we're sure we can't do it. And yellow means you're getting close to the limit of the system, so let's get the technical guys involved to assess that particular application to make sure we're on the right side of the line. So that was CO2 in nitrogen. This one down here is CO2 in methane. We have never measured CO2 in methane. Our customers do, and we get results, but we haven't got a facility back in Cambridge, UK, to measure CO2 and methane. But we can calculate from the physics what it does. This is another example. This one is methane in nitrogen. So this, again, you've got 44-inch pipe over there, 100% nitrogen, methane. We can do all of these. This is getting close to the limit, so we'd bring in the R&D folks. But this one has nothing to do with CO2. This is methane and nitrogen, but we can extrapolate using the physics from the CO2 measurement to another gas composition. So these are only binary combinations. You can put all 20 gases in if you like, and it just prints out these charts. So that we think is a pretty unique facility that we have. So we've got a lot of test data from different facilities around the world. That all feeds into the physics model, and you get this. So really, that's the end of the CO2 story. We've been working on this for a number of years. We've developed new transducers, new electronics, new signal processing, all focused on pushing the boundary of the measurement of CO2 or measurement of gases containing high amounts of CO2. Like if you must be non-intrusive, then the limit here is 100% CO2 in a 16-inch diameter pipe. And because we've got this capability now, we're in a position via people like Christopher to help you measure your gases which contain high CO2 and give you highly accurate and reliable results. Not quite the end of the story. If you weren't interested in one of these two things, hydrogen measurement and emissions, then I guess you wouldn't be here at this conference. CO2, where I hope we're at the end of the road. We've probably still got some improvements we can make, like we're going to do in end of April, but these are our next focus points. Hydrogen, I've already mentioned, is a very difficult gas because of the high speed of sound. And of course, flare efficiency. I don't need to say anything about that because everyone else in this conference is doing that. So in future conferences, you might be hearing about these two topics. So thank you very much for listening. I hope that's been of interest and you've learned something about the nitty-gritty of ultrasonic flare measurement. So I don't know how we are for time, Christopher, but I'm more than happy to take questions, or you can come by the booth, which Christopher's manning later in the day. Thank you. Thank you for your attention. Thank you. Nice to have a bit of physics, eh?
I just learned this morning that stock order and apartments that are coming in. 10-year variant. Once we're not scheduled to show up. And what's that? We're trying to schedule installation of those. They're all right now.
Okay.
I'm kind of working. Could you shut down the Teams meeting afternoon?
I'm sorry.
Could you shut down the Teams meeting? It may be recorded when I'm saying. But that's actually happening right now. Regarding whether it's going to work or not, I think Dr. Neal explained the product tool that we use to determine which stuff works, which stuff doesn't work.